is no longer a limiting factor in the growth of civilization. Governments, research organizations, and companies all across the world are racing to achieve a fusion power breakthrough. It would mean the end of fossil fuels, a technology so impactful, its invention could be compared to man's earliest control of fire. Many critics say it's impossible, but one company believes they've cracked the code.
So David, are you building a machine that will produce cheap, clean, abundant energy in our lifetime?
That's the goal. So Helion Energy is building fusion generators. Our goal is to build 50 megawatt scale generators that generate clean, safe electricity.
According to Helion, your home might be powered by fusion much sooner than anyone expected. But why is fusion considered the holy grail of energy? If you could design the perfect energy source, it would have an inexhaustible supply of fuel, be environmentally friendly, not take up much space, and have a high degree of safety. Fusion power, an experimental form of power generation that harnesses the energy released when two atoms combine, fits the bill. Research into fusion power began in the 1950s, and scientists have been able to fuse atoms in a laboratory setting for decades. But no one has yet been able to demonstrate fusion in a practical way to generate electricity. The potential is enormous. Just 1 gram of Helion's fusion-fueled deuterium contains enough energy to power a home for an entire year, and its supply is virtually unlimited, found in small concentrations in all water on Earth.
I can't take it anymore, Mr. Nibbles. It's always, yo, Death Knight, buff my armor. Hey, Death Knight, get your...
The fuels considered for fusion power have traditionally all been isotopes of hydrogen, protium, deuterium, and tritium.
And what we saw is that there's some better fusion reactions. And deuterium and a rare isotope of helium called helium-3, and you fuse those together and you make helium-4 and a tremendous amount of electricity.
But what is nuclear fusion? How can just 1 glass of anything contain as much energy as 10 million pounds of coal? To answer that, we must enter the inconceivably small and impossibly strange world of the atom. The atom is the smallest unit of ordinary matter that forms every element in the universe. Every atom is composed of a nucleus and 1 or more electrons. If we zoom into the nucleus, we'll find it's made up of protons and neutrons. Because neutrons are neutral, nuclei are positively charged. If you heat atoms to high enough temperatures, they lose their electrons, forming a hot cloud of charged particles called a plasma. Atoms are always moving, vibrating, and bouncing around. The denser the plasma, the more likely it is that nuclei will collide, but positively charged nuclei repel each other if they get too close. The hotter the plasma, the faster the charged particles move, and the faster a particle is moving, the more kinetic energy it has. When nuclei collide at high enough speeds to overpower their electrostatic repulsion, they can get close enough to be overcome by a stronger attractive force, called the strong nuclear force, and they snap together. When 2 light nuclei combine to form 1 heavier element, the reaction is known as nuclear fusion. This element weighs slightly less than the sum of its parts. The missing mass, or deficit, was released as pure energy, up to 4 million times more energy than burning fossil fuels. In the core of the sun, gravity produces incredibly high pressures, compressing elements to densities higher than the heaviest metals and to temperatures over 15 million degrees Celsius, perfectly extreme conditions for hydrogen to fuse into helium. The sun is Earth's largest source of energy. Plants convert sunlight into chemical energy with photosynthesis, and we release it by burning fossil fuels. Solar radiation powers the wind that spins our windmills, the rivers that drive our turbines, and we can even convert sunlight directly to electricity with photovoltaics. It's about time we vertically integrate and bring nuclear fusion in-house. But without the benefit of tremendous gravitational forces and 10 billion years worth of fuel, man-made fusion will need to be even hotter and more efficient than the sun. In a man-made fusion device, you must not only confine a plasma so hot it will vaporize anything it touches, but also harness this chaotic thermonuclear reaction to generate more energy than is being lost to the environment.
And that's the critical parameter of, did you make a fusion fuel dense enough? Are the particles close enough together? Are they hot enough so that they can actually react with each other? And are they around long enough to create a lot of reactions?
It turns out, bottling a star is one of the most difficult technical endeavors ever attempted on Earth.
So I think the hardest part about fusion is that we have a combination of engineering and physics disciplines that all come together, and they all have to work. And so you have not only the complex physics around the electromagnets and the fusion plasmas itself, but you also have these systems that operate at high temperature, high stress, high pressure. And most importantly, you have to do it in a way that's commercially relevant.
Helion's key to solving the ultimate energy puzzle is contained in these purple glowing rings that are fired at over 1 million miles per hour. But there's more than one way to fuse an atom. In fusion, there's 3 key groups of approaches. In magnetic fusion, the goal is to contain a very hot plasma in a steady magnetic field for a long time, until it ignites and forms a self-propagating fusion reaction. In contrast, inertial confinement fusion relies on achieving higher plasma densities. Fusion is initiated by rapidly compressing and heating tiny targets filled with fusion fuel, most often using high-energy lasers. Each shot takes place in 1/1000th of a second.
And there's a third type of fusion called magnetoinertial fusion that takes both worlds. And you magnetically confine and contain a plasma, like we do in our field reverse configuration. And rather than trying to hold on to it for a very long time, you compress and heat it, add energy through compression. And in our case, you end up right about in the middle, where it all happens in about 1/1000th of a second.
While fusion reactions have been successfully demonstrated by various approaches,